Good morning, everyone. A very warm welcome to our keynote speaker, Dr. Paresh Patel, sir, from Veer Narmad South Gujarat University, Surat. I welcome you all the participants present on this webinar. I, Dr. Khushbu Desai, on behalf of KBS Commerce and Natraj Professional Sciences Colleges, welcome you all on today's webinar on symmetry and group theory and its application. Uh, the basic objective of this webinar is to provide you with a comprehensive overview of symmetry and group theory and its application. Over to you, Mr. Abhishek Patel.
Thank you, ma'am. It is a great honor and matter of pride to introduce our eminent keynote speaker, Dr. Paresh S. Patel. He has been working at the Post-Graduation Department of Chemistry, Veer Narmad, South Gujarat University, Surat, and presently holds the post of professor. He received his master's and PhD in organic chemistry. Sir has 25 years teaching experience in the field of chemistry and is specialized in organic chemistry, reaction mechanism, pericyclic reaction, photochemistry, natural products, rearrangement, and molecular symmetry, and many more subjects. His research interest includes synthetic organic chemistry, dyes, drugs, and polymers. He has published about 51 research papers in various reputed national and international journals. Recently, he is supervising 7 research scholars while 7 candidates have completed their PhD research under his guidance. He has served as investigator of a major research project funded by the University Grant Commission, India. Sir is serving as a life member of an Indian Chemical Society and Indian Council of Chemists, and he is also serving as a member of board of study School of Science at PP Savani University, Surat. Sir also has delivered many invited talk expert lectures at various universities in Gujarat state. He served as a resource person in one-day workshop under Odisha KCG Education Department, Government of Gujarat. Dr. Patel has also been judged at national and international and state level conferences and seminars. Thank you very much, sir, being with us and providing your valuable time with us. Thank you very much, sir.
Thank you. First of all, the management of the KBS College, principals of the KBS College, Dr. Poonam Ben Chauhan Madam, head of the department, Dr. Khushbu Desai Madam, and for nice introduction, Abhishek Bhai, to give me opportunity and invite me to deliver the lecture on this symmetry. So thank you very much. So good morning, one and all. So happy New Year to all of you. So dear students, today we are going for the one unit in inorganic chemistry, and the title of our unit is Symmetry and Group Theory in Chemistry and its Application. So before starting our topic, I would like to say something general introduction of regarding the molecular symmetry. So dear students, you know very well about this symmetry, the correspondence of a figure with reference to plane, line, and point of a symmetry. And we know that the most of the things in the natures are very beautiful, and the beauty of that nature things due to the molecular symmetry. Due to the symmetry, just like a sun, moon, these are the classical examples of the natural symmetry. So this type of the symmetry arises in our molecules. So that type of the symmetry can be recognized as a molecular symmetry. So let us start first with the symmetry. So please, presentations. Kusu madam, please go for the presentations.
Ji, sir.
Now, first of all, the molecular symmetry and group theory in chemistry and its applications. Before starting this, I would like to say something general introduction part of the symmetry. So we already discussed about the general introduction about the symmetry. So these are the beautiful things, and the beauty of the all these things is due to the symmetry. And this type of the symmetry arises in our molecule, that is known as a molecular symmetry. So this is the beautiful Taj Mahal, and the beauty of this Taj Mahal is due to its symmetry. This some of the symmetry arise in our molecule. So that type of the symmetry can be recognized as a molecular symmetry. Suppose the first example is the hydrogen. We know that in case of the hydrogen, Kusu madam, in case of the hydrogen molecule, if we rotate this molecule along the imaginary axis around 180 to give equivalent orientation of this molecule. So this sum of the symmetry is due to the proper axis of symmetry. So anyhow, this is the classical examples of the molecular symmetry. Now, in case of the molecular symmetry, axis, plane, and point, these are known as the symmetry elements, and the process is carried out on the basis of axis, point, and line to get the equivalent orientation position are known as a symmetry operation. So what is symmetry operation? The process is carried out on a plane, line, or point to get the equivalent orientation position. So is known as symmetry operation. And what are symmetry elements? We already discussed about these symmetry elements: point, lines, and points. Planes, lines, and points. These are known as the symmetry elements. So let us start with the symmetry elements and symmetry operations. So first symmetry element is the identity. Identity can be represented by capital E. E means inert. It means do nothing. So each and every molecule consists identity symmetry element, and if we operate identity symmetry operation on any molecule, molecule remains as it is. There is no change in the position of the molecules. So first symmetry element is identity, and if we operate identity symmetry operation, molecule remains as it is. There is no change. Second symmetry element is the proper axis of symmetry, and this proper axis of symmetry element can be represented by Cn, and where n is equal to order of axis. If we rotate any molecule around 180, so 360 by 2, 180 is equal to 2. So order of axis of that molecule is 2. In case of, if you rotate the molecule around 120, so in that case 360 divided by 3, it means order of axis is equal to 3. If we rotate any molecule around 90, so in that case n is equal to 4. In case of the 60, it is 6. So order of axis can be represented by 360 divided by theta. So let us start with the first example is the water molecule. We know that the shape of the water molecule is a V shape, and this one is the imaginary axis, and along this axis, if we rotate these molecules around 180 to get the equivalent orientation position, it means here theta is equal to 180. Means to get the equivalent orientation position, we have to rotate these molecules along this imaginary axis around 180. It means here n is equal to 2. Why? N is equal to 360 divided by 180. So n is equal to 2. It means order of axis for water molecule is equal to 2. In case of ammonia molecule, here we have to rotate this molecule. This shape of this molecule is a pyramidal. This one is the imaginary axis, and according to this imaginary axis, if we rotate these molecules along this imaginary axis around 120 to get the equivalent orientation position. So here In case of the ammonia molecule, n is equal to 360 by 120, so is equal to 3. So in case of the ammonia molecule, order of axis is equal to 3. This is a twofold axis of rotation, means we already discussed in case of the water molecule. Now this is the another molecule, BF3 molecule. The shape of these molecules is a planar structure. Okay. Now in this case, this is the imaginary axis. This is the imaginary axis, and if we rotate these molecules along this imaginary axis around 120 to get the equivalent orientation position. So in case of the BF3 molecule, n is equal to 360 by 120. It means order of axis for this molecule is equal to 3. And in this case, n is equal to 3, means order of axis is equal to 3. In case of the BF3 molecules, the one axis is C3. It means symmetry element is C3. And if we rotate, these are also imaginary axis. But according to this imaginary axis, if we rotate these molecules around 180 to get the equivalent orientation position. So in case of the BF3 molecule, one axis is C3 and remainings are these C2. Now in case of molecular symmetry, higher order of axis can be considered as a main principal axis. So in case of the BF3 molecule, main principal axis is C3. Why? The order of C3 is higher than C2. So in case of the BF3 molecule, one C3 is present and three C2s are perpendicular to the C2 axis. So in case of the BF3 molecules, main principal axis is C3 and C3 is perpendicular to 3 C2s. Now, in case of order of axis are the same, then which one is the main principal axis? So in that case, if order of axis are the same, then the axis passes to numbers of the atoms that can be considered as a main principal axis. So this is the symmetry elements in case of the BF3 molecule. This is the cyclobutane molecule. In case of the cyclobutane molecule, if we rotate these molecules around 90 along this imaginary axis, this is the imaginary axis, and if we rotate this molecule around this imaginary axis around about 90 to get the equivalent rotation position. So C4 is a symmetry element, and C41, C42, C43, C44, these are the symmetry operations. So dear students, remember that C4 is a symmetry element, and C41, C42, C43, these are the symmetry operations. This is cyclopentadiene. In case of the cyclopentadiene, the imaginary axis, this one is the one imaginary axis, and if we rotate these molecules around this along this imaginary axis around 72 to get the equivalent rotation position. So in case of the cyclopentene, order of axis n is equal to 360 by 72 is equal to 5. It means symmetry element is a C5. It means order of axis is equal to 5. It means symmetry element is C5. And symmetry operation can be represented as a C51, C52, etc. In case of the cyclopentadiene, the another imaginary axis are also present, and that imaginary axis are perpendicular to the C5. And if you rotate this molecule along this axis around 180 to get the equivalent rotation position, it means in case of the cyclopentadiene, main principal axis is C5 and C5 is perpendicular to 5 C2s. This is benzene molecule. In case of the benzene molecule, if we rotate these molecules along this imaginary axis around 60 to get the equivalent orientation position. So in case of the benzene molecule, Order of axis n is equal to 360 by 60 is equal to 6. That means C6 is the symmetry element, and C61, C62, C63, C64, C65, C66, these are the symmetry element, symmetry operations. Now, in case of the benzene molecules, one imaginary axis, or we can say order of symmetry element is C6, and 6 C2s are perpendicular to the main principal axis. So, in case of the benzene molecule, 6 C2s are present. This is 3-4 axis we already discussed in the BF3 molecule. Now, this is the rotation. So, what will happen regarding the symmetry operations? This one is the BF3 molecule. In case of the BF3 molecule, if we rotate this molecule, this is the main principal axis as a C3. And if we rotate these molecules along this main imaginary axis, main principal axis around 120 to get the equivalent orientation position. So these symmetry operations can be represented as C31, C32, C33, etc. Okay. In case of the BF3 molecule, main principal axis is C6, and 3 C2s are perpendicular to the main principal axis. In case of NiCN4-2 complex, this is the imaginary axis, and if you rotate these molecules along this imaginary axis around 90 to get the equivalent rotation position, it means in case of the NiCN4-2 complex, main principal axis is C4. Why C4? Here order of axis n is equal to 360 by 90. So n is equal to 4. And these are the another imaginary axis. And along this imaginary axis, if we rotate this molecule around this imaginary axis about 180 to get the equivalent rotation position, it means in case of the NiCN4-2 complex, main principal axis is C4, and 4 C2s are perpendicular to the main principal axis. So again, repeat that. So dear students, remember that higher order of axis proceed as a main principal axis, but the order of axis are the same. So in that case, so axis passes to the numbers of the maximum numbers of the atom that can be considered as a main principal axis. Another example is the benzene molecule. In benzene molecule, this is the imaginary axis, and this imaginary axis can be represented as a C6. This is in case of the PF5 molecules, and these are the 6 C2s are perpendicular to the benzene molecule. Now this is BF3 molecule we already discussed. Yes, this is PtCl4-2 complex, and the shape of this molecule is a square planar. So in this case, this is the imaginary axis. So red line represents, this is the principal axis, this is the imaginary axis, and along this imaginary axis, if we rotate these molecules along this imaginary axis around 90 to get the equivalent rotation position, it means n is equal to 4. It means main principal axis is C4. Similarly, these are the 1, 2, 3, and 4. These are the another imaginary axis, and along this imaginary axis, if we rotate these molecules around 180 to get the equivalent rotation position, so these are known as a C2. Why C2? Here order of axis is equal to 360 by 180, so n is equal to 2. So in case of the PtCl4-2 complex, main principal axis is C4, and C4 is perpendicular to 4 C2. These are the 4 C2s. Now in case of the PF5 molecule, FeCO5 molecule, this is very similar to our PF5 molecule. Now the shape of this FeCO5 molecule is a trigonal bipyramid. This one is the imaginary axis, and along this imaginary axis, if we rotate these molecules along this imaginary axis around 120 to get the equivalent rotation position. So here n is equal to 3, and main principal axis is C3. why the order of axis of C3 is higher than C2's. So in case of the FeCO5, these are the 1, 2, and 3. These are the C2. Why C2s? If we rotate these molecules along this axis around 120 to get the equivalent orientation position. So in case of the FeCO5, main principal axis is C3 and 3 C2s are perpendicular to the main principal axis. Now, second type of the symmetry element, we already discussed about the identity and proper axis of symmetry. Now, third type of the symmetry element is a plane of symmetry, and plane of symmetry can be represented by sigma. Now, what is plane of symmetry? We have to image a plane, and with the help of this plane, we have to divide the molecule by this imaginary plane in such a way that one part is the mirror image of the another part of the molecule. So that type of the symmetry can be recognized as a plane of symmetry. So dear students, what is plane of symmetry? We have to image a mirror or plane, and with the help of that mirror or plane, which can bisect or which can divide or bisect the molecule in such a way that one part is the mirror image of the another part of the molecule. So that type of the symmetry can be recognized as a plane of symmetry. Now, plane of symmetry can be divided into three parts, or we can say plane of symmetry can be classified into three categories. First one is vertical plane of symmetry. Second one is horizontal plane of symmetry, and third one is diagonal or dihedral plane of symmetry. Now, first one is vertical plane of symmetry. Vertical plane of symmetry can be symbolized as a sigma v. Now, what is vertical plane of symmetry? If plane is parallel to main principal axis, so that type of the plane of symmetry can be recognized as a vertical plane of symmetry. So dear students, remember that if plane is parallel to main principal axis, so that type of the plane of symmetry can be recognized as a vertical plane of symmetry. As for example, this is water molecule. Water molecule consists two types of the vertical planes. So both these planes are parallel to main principal axis. This is the imaginary axis, and along this imaginary axis, if we rotate these molecules along this imaginary axis around 180 to get the equivalent orientation position. So these two planes are parallel to main principal axis. So both are the examples of the vertical planes. Now, these planes can be recognized as a sigma xz plane. Why xz plane? Because this one is parallel to x and this one is parallel to z. So this plane can be recognized as a sigma xz plane. And this plane can be recognized as a sigma yz plane. This is parallel to y and this edge is parallel to z. So this plane can be recognized as a sigma yz plane. Water molecule consists two planes, sigma v xz plane and sigma v yz plane. So in case of sigma v xz plane, this is known as a molecular plane, or we can say it is available in a molecule. So that's why this plane can be recognized as a sigma v xz, or we can say molecular plane. And by operating sigma v xz symmetry operation, molecule remains as it is. There is no change in the position of the hydrogen in case of the water molecule. Now, the another plane is the sigma yz plane. This is sigma yz plane, and with the help of this sigma yz plane, which can bisect the molecule, one part is the mirror image of the another part of the molecule. It means if we operate sigma yz symmetry operation to change the position of the both these hydrogens. So these are the basic difference between sigma xz plane and sigma yz plane. So first one is sigma xz plane. So there is no change in the position of these hydrogens. And second one is the sigma yz plane. So this is the difference between sigma xz and sigma yz symmetry operation. So dear students, in case of the water molecule, we have to remember that water molecule consists one identity symmetry element, one C2 axis of symmetry element, and two vertical planes, and two vertical planes are sigma xz planes and sigma yz planes. In case of, if you operate identity symmetry operation, there is no change in the position of the hydrogen. But if we operate sigma xz symmetry operation, there is no change in the position of the hydrogen. But if we operate sigma yz symmetry operation, so to change the position of the hydrogens. Okay, so dear students, in our this topic we have to remember the symmetry elements of the water molecule. Water molecule consists four symmetry elements: identity, C2 or C21, sigma vxz and sigma yz symmetry elements. This is ammonia molecule. The shape of the ammonia molecule is a pyramidal, and ammonia molecule consists three vertical planes, and all the three planes are parallel to main principal axis. This is the imaginary axis, and this is threefold axis of symmetry, or we can say here order of axis is equal to 3, and all the three planes are parallel to main principal axis. It means all the three planes in the ammonia molecules are the examples of the vertical planes. Okay, now in case of the ammonia molecule, if we operate sigma v1, so the position of the hydrogen in sigma v1 remains as it is, and to change the position of the hydrogens in sigma v2 and sigma v3. Okay, so dear students, remember that in case of the ammonia molecule, the shape of the ammonia molecule is a pyramidal, and ammonia molecule consists three symmetry vertical planes: sigma v1, sigma v2, sigma v3, and all the three planes are parallel to main principal axis. And if we operate symmetry operation, suppose sigma v1, so the hydrogen of the sigma v1 remains as it is, there is no change. And if you operate sigma v1 to change the position of the hydrogen 2 and 3, this is another type of the plane of symmetry, and this is known as horizontal plane of symmetry. In case of the vertical planes, we already discussed that if the plane is parallel to main principal axis, so that type of the plane of symmetry can be recognized as the vertical plane of symmetry. In case of horizontal plane of symmetry, horizontal plane of symmetry can be symbolized by sigma h. If plane is perpendicular to the main principal axis, so that type of the plane of symmetry can be recognized as the horizontal plane of symmetry. And if we operate sigma h symmetry operation, so there is no change in the position of the molecule. This is BF3 molecule, and we already discussed that this is planar molecule. This is the imaginary axis, and this plane is perpendicular to the main principal axis. It means this plane is sigma h. Or we can say if we put a mirror instead of this plane, so there is no change in the position of the all these boron fluorine atoms. So this is the horizontal plane of symmetry in case of the BF3 molecules. In case of the PF5 molecule, the shape of the PF5 molecule is a trigonal bipyramid, and this is the main principal axis is C3, and these are the three C2s. Now third one is diagonal plane of symmetry. In this plane, diagonal plane of symmetry, this can be symbolized by sigma d. Now what is diagonal plane of symmetry? This is the imaginary plane which can bisect the main principal axis as well as C2 in such a way that one part is a mirror image of the another part of the molecule. So in case of the alene molecule, this is alene molecules, C double bond C, and two terminal hydrogens at the each terminal carbonate. This is the alene molecule. This is the C2 axis as well as this is also C2. Actually, this one is the main principal axis. In case of the alene molecule, three C2s are there: one C2, second C2, and third C2. Out of them, this can be represented as a main principal axis. In case of the alene molecule, the order of axis of all the axes are the same, C2. But which one is the main principal axis? This one is the main principal axis. Why? This can pass this can pass to the 3 atoms. It means this one is the main principal axis. All are the C2s, but this one is the main principal axis. Now, if you put a mirror over here, which can bisect the C2 as well as main principal axis in such a way that this part is the mirror image of the another part of the molecule. So this type of the plane of symmetry can be recognized as diagonal plane of symmetry. So in case of this is water molecule and this is again water molecule. Fourth symmetry element is the center of symmetry. This is the imaginary point in the center of a molecule through which the reflection each atom can be carried out to result in its coincidence with an equivalent atom. Means in case of the center of symmetry or point of a symmetry, we have to image a point, and with the help of that point we can inversify each and every atom of the molecule. And if we operate center of symmetry to inversify the molecule, this can be symbolized by this small I. This is the center of inversion and symmetry operation of center of inversion. So we can inversify each and every element of the molecule. This is the center of symmetry in I as well as trans dichloroethylene. So we can inversify this molecule by operating center of symmetry operation. Now last symmetry element is the improper axis of symmetry, or we can say rotational reflection axis of symmetry. Now, what is improper axis of symmetry or rotational reflection axis of symmetry? This is an axis passes through the molecule on which molecule has to be rotated by 2 pi by an angle and reflect on a plane of perpendicular to the rotational axis to stay in the equivalent orientation. This axis of proper rotation can be represented by Sn. Now, what is improper axis of symmetry? We have to image a imaginary axis, and if we rotate the molecule around theta and then reflect to the horizontal plane, that is sigma h, to get the equivalent orientation position. So this type of the symmetry element can be represented as a improper axis of symmetry or rotational reflection axis of symmetry. Now this is the reflection axis, rotation reflection axis in tetrahedral structures, just like a methane molecules. And okay, in case of improper axis of rotation, we have to rotate these molecules around theta and then reflection through horizontal plane to get the equivalent orientation position. In case of the trans dichloroethylene, if we rotate the molecule along the main principal axis around 180 and then reflection through horizontal plane to get the equivalent orientation position. So I think this is the introduction part of the molecular symmetry. So dear students, now we are going for the how to assign a point group of any molecule. So with the help of one chart, we can assign a point group to the any molecules. So let us start with the point groups. Now, what is point group? The collection of a different symmetry elements and their related symmetry operation can be represented by point group. Okay, so point group is nothing but the collection of a symmetry elements and their related symmetry operations. According to the showing flash, we can assign a point group to the any molecule. So how to assign a point group to the any molecule. So dear students, this is very important title for many competitive exams, just like a NET, GATE, SET, as well as PAT examinations. So always one question arises from the point group. So how to assign point group of any molecule, that is most important title. So let us start how to find out the point group of any molecule. So let us start with the is a molecule linear? First of all, we have to ask questions to the molecule. Is the molecule linear? Then we have to ask no or yes. If it is yes, then C infinite V or D infinite H point groups may be present. If yes, then sigma V is present, then point group can be assigned as a C infinite V. If sigma H is present, then D infinite H point group can be assigned. Okay, so how to assign a molecular point group to the any molecule? So first of all, we have to make a question: is the molecule linear or non-linear? So non-linear, then we have to go for the another question: any multiple higher order exist. Any multiple higher order axes are present. So dear students, remember that multiple means minimum multiple is 3. We can ask about 4C3, 3C3, 6C3s, 5C4. So out of them, 3 can be represented as a multiple. And higher order, we already discussed about the how to find out the order of axis. So for this multiple hard order axis, the minimum criteria to be a multiple hard order axis is 3C3. This is the minimum criteria to be a multiple high order axis of symmetry. So next question is any multiple hard order axis. So we have to make a question that yes and no. Yes, then CD or OH point group may be present. And if sigma D is present, then point group can be assigned as a TD. If sigma H is present, then point group OH can be assigned. If no, then we have to make a questions any proper, improper axis are there. So we have to ask questions. Any proper, improper axis? Improper. Then SN point group can be assigned. No. Then we have to ask questions. Improper axis. Any proper, improper axis? Yes, improper. C1, CS, or C. C1, CS, or CI. Yes. Improper and proper. In case of sigma is present, then point group can be assigned as a CS. I is present, then point group can be assigned as a CI. Both are absent, then point group can be assigned as a C1. Improper, that is acid. Proper axis, so we have to make another question. Cn is perpendicular to NC2. So we have to go for the yes and no. Dn, DNH, DND, DNV. Cn, CNV, CND, CNH. Okay. Now, in case of the D option, sigma H is present, so DNH. Sigma V is present, then DNV. Sigma D is present, then DND. All are absent, then point group can be assigned as a DN. Now, in case of sigma H is present, then CNH. Sigma V is present, then CNV. Sigma D is present, then CND. All are absent, then CN. So, dear students, with the help of this chart, we can assign a molecular point group to the any molecules. So, let us start first with the is a molecule linear or non-linear. If it is a linear, and this is non-linear. Okay, if it is linear, then C infinite V or D infinite H point group can be assigned. If sigma V is present, then point group can be assigned as a C infinite V. Sigma H is present, then point group can be assigned as a C D infinite H. Now, in case of if it is non-linear, molecule is a non-linear, then we have to make another question. Any multiple order axes are present? If yes, then TDOH point group can be assigned. Multiple order axes are option, then we have to make another question. Any proper improper axis? If yes, no. Proper and improper axis are option, then C1, CS or CI point group may be present. If sigma H is present, then it can be assigned as a CS. If I is present, then point group can be assigned as a CI. Both are absent, then C1 can be assigned. Okay. Any proper improper axis? Yes. Improper axis, then SN point group can be present. And if proper axis are present, then we have to make a question. N is equal to order of axis. Dn is perpendicular to NC2. Yes. Then point group can be assigned as a Dn, DNS, DND, or DNV. Okay, in that case, sigma H is present, then point group can be assigned as a DNH. Sigma V is present, then DNV point group can be assigned. Sigma D is present, then DND point group can be assigned. Okay, all are absent, then point group can be assigned as a DN. Similarly, in case of the CN doesn't perpendicular to NC2, so we have to go for the CN, CNV, CND, and CNH option. So in that case, if sigma H is present, then CNH point group can be assigned. Sigma V is present, then CNV point group can be assigned. Sigma D is present, then CND, and all are absent, then only CN point group can be present. So let us start with the examples. So first example is this is carbon monoxide. We know that carbon monoxide is a linear molecule. Carbon monoxide is a linear molecule. In case of the carbon monoxide, the plane is parallel to main principal axis. It means vertical plane is present. So according to this chart, first of all, we have to make a question. Is a molecule linear? Yes. Carbon monoxide molecule is a linear. It means we have to go for this option, C infinite V and D infinite H. Now, in case of the carbon monoxide, sigma V is present, means C infinite V point group can be assigned. Okay. So, dear students, we have to write down that carbon monoxide is a linear. So, C infinite V or D infinite H point groups may be present. But sigma V is present, means point group of carbon monoxide is a C infinite V. Another molecule is hydrochloric acid. In case of the hydrochloric acid, this is again linear. So this is very similar to carbon monoxide. This is carbon dioxide. In case of the carbon dioxide, this is linear molecule. So according to this chart, is the molecule linear? Yes, this is linear. It means C infinite V or D infinite H point groups may be present. But here, the plane is perpendicular to the main principal axis. It means this plane is a sigma H. It means D infinite H point group is present in case of the carbon dioxide. So we have to assign D infinite H point groups to the carbon dioxide molecules. Classical examples are men, seizure, pipette. These are the examples of the C infinite V point groups. So dear students, remember that in all the cases, man, seizure, pipette, in that case, these are the linears and main principal axis is parallel to the plane. So C infinite V point group may be present. Now, next molecule is a methane molecule. Methane molecule is a tetrahedral. The shape of the methane molecule is a tetrahedral. Okay, it means it is a non-linear. So we have to keep this one linear portion. So we have to go for the non-linear. So in that one, we have to make equations. Any multiple harder axes are present. So in case of the methane molecule consists E, 4C3, sigma D, etc. symmetry elements. So here, multiple, it means 4. And we already discussed that to be a multiple hard axis, the minimum criteria is 3C3. 3C3 is the minimum criteria to be a multiple hard axis. So here 4C3, it means multiple hard axes are present in case of the ammonia molecule, in case of the methane molecule. Now, here sigma D is present. It means point group can be assigned as a TD. So methane molecule consists TD point group. Next one is SF6 molecule. The shape of the SF6 molecule is a octahedral. Shape of the SF6 molecule is a octahedral. This molecule consists E, 3C4, sigma H, etc. symmetry elements. So dear students, we know that SF6 molecule is a non-linear, or we can say this is octahedral. So we have to skip this portion, linear portions. So non-linear. So we have to make another equation. Any multiple harder present? Yes. Then TD or OH point group may be present. But here sigma H is present. So point group is OH. So in case of the SF6 molecule, point group can be assigned as a OH. Why? The shape of this molecule is an octahedral or sigma H is present. Another molecule is hypochlorous acid. We know that how to generate hypochlorous acid. If we pass chlorine gas through water to generate hypochlorous acid as well as hydrochloric acid. Now, the shape of this molecule is planar. But in this hypochlorous acid, there is no proper improper axis are present. So let us start with the first question. Is it linear or non-linear? So we have to make answer that non-linear. Means we have to skip this linear portions. Any multiple order axis? So there is no even any proper or improper axis. It means multiple order axis are absent. It means TDOH are absent. Any proper or improper axis? No. Proper and improper axis are absent. So we have to go for this option, C1, CS, and Ci. So we have to mention that here sigma H is present. This is planar. It means point group is CS. So dear students, we have to go for this chart, follow this chart. First of all, we have to make a question, is a linear or non-linear? Yes, it is a non-linear. Then we have to make a questions, any multiple order axes are present? No, multiple higher order axes are absent. Any proper improper axis? Proper and improper axis are also options. Then we have to go for these options, C1, CS, and Ci. So here, H, sigma H is present. Why? This is planar molecule. So point group can be assigned as a CS. This is trans difluoroethane. This is Newmanson projection diagram. Okay. So is it linear? This molecule is a non-linear. Then we have to make a questions. Any multiple order axes are present? No, multiple order axes are also absent. Means we have to go for the any proper improper. So there is no any proper improper axes are present in the trans difluoroethane. So we have to go for this option, C1, CS, or Ci. So here sigma H is absent, but I is present. Right? This carbon chlorine bond can be inversified by carbon fluorine bond. Carbon fluorine bond can be inversified by carbon fluorine bond, and carbon hydrogen bond can be inversified by carbon hydrogen bonds. So I is present. So point group is Ci. Next molecule is C, X, Y, Z, W. All are the different X, Y, Z, and W. These are the different substituents. And we know that methane molecule is a tetrahedral, and this is the different substituted methane derivatives. It means this is non-linear. Multiple order axes are also absent, and proper improper axes are also absent. Means we have to go for this option, C1, CS, or Ci. But sigma H and sigma H and I both are absent. It means point group is C1. Next molecule is water molecule. So dear students, we have to remember that in case of the water molecule, symmetry elements are C, C2, sigma Vxz, sigma Vyz symmetry elements. Okay. We know that the shape of the water molecule is a V shape, and it is a non-linear. Multiple order axes are absent. Why? Water molecule consists only one C2. It means multiple order axes are also absent. Any proper improper? Yes, proper axis is present. Only one C2 is there. So proper axis means we have to make a question. C2 thus perpendicular to 2C2. C2 doesn't perpendicular to 2C2s. So water molecule consists only one proper axis, that is C2. It means C2 doesn't perpendicular to 2C2s. It means we have to go for the C option. If Cn is perpendicular to NC2, then we have to go for the B option. If Cn doesn't perpendicular to NC2, then we have to go for the C option. So here n is equal to order of axis. In case of the water molecule, order of axis is equal to 2. And two vertical planes are present. Two vertical planes are present. It means C2V. C2V point group is present in case of the water molecule. So dear students, we have to follow this chart. So first of all, we have to go for the molecule is a linear, non-linear, and then multiple Harvard axis, then proper, improper axis. In case of the proper axis, we have to make a equation Cn doesn't Cn is perpendicular to NC2, and then we have to go for the D option, either D option or C option. Next molecule is ammonia molecule. So, dear students, we have to remember the symmetry elements of the ammonia molecules as well as water molecules. Ammonia molecule consists E2C3. 2C3, it means C31, C32 or C3 plus C3 minus, and 3 sigma V. 3 sigma V may be sigma V1, sigma V2, sigma V3 or sigma VA, sigma VB, sigma VC. So this is non-linear. The shape of this ammonia molecule is a pyramidal. It means this molecule is a non-linear. Means we have to go for the next question. Any multiple harder axis? No. It consists only 2C3. So it is not considered as a multiple harder axis molecule. Next question, any proper, improper? Yes. It consists proper axis. Which proper axis? 2C3s. But C3 doesn't perpendicular to 3C2s. Okay. So ammonia molecule consists only C3 plus C3 minus or C31, C31. There is no C2. It means we have to go for the C option. Here order of axis is equal to 2. Here, 3. Here order of axis is equal to 3. And 3 vertical planes are present. It means we have to go for the C3V. N is equal to 3 and vertical planes are present. It means point group is C3V. Next molecule is BF3 molecule. The shape of this BF3 molecule is a planar. So this molecule consists E twice C3, 3 C2s, sigma H, and etc. So first of all, is it linear or non-linear? This is non-linear. Any multiple order axis? No. This is multiple 2. It means it is not considered as a multiple harder axis molecule. So multiple harder axis are option. Then we have to make a questions. Any proper, improper axis? Yes, proper axis. Then we have to go for the C3. Thus perpendicular to 3C2. Yes. In case of the BF3 molecule, C3 is perpendicular. So we have to mention over here C3 is perpendicular to 3C2s. It means we have to go for the D option. So DN, DNH, DND or DNV. Here order of axis is equal to 3. It means D3, D3H, D3D or D3V. But here sigma H is present, means point group is D3H. So BF3 molecule consists D3H point group. Another molecule is benzene ring. In case of the benzene ring, C6, this is the main principal axis, and C6 is perpendicular to 6 C2s, sigma H, and etc. Okay, benzene is a planar molecule. It is a non-linear, means C infinite V, D infinite H point groups are absent. Then we have to go for the any proper, improper axis. Yes, proper axis. Which proper axis? C6 proper axis. Then we have to make equations. C6 is perpendicular to 62. C6 is perpendicular to 62. Yes. So we have to go for this D option. Otherwise, we have to go for C option. Okay. If C6 doesn't perpendicular C62, then we have to go for the C option. But here, C6 perpendicular to 62 means we have to go for the D option. Here, order of x is equal to 6 means D6, D6H, D6D, D6V. So n is equal to 6. And horizontal plane is present. It means point group is D6H. This is trans-dichloroethylene. In case of the trans-dichloroethylene, this molecule consists E, C2, sigma H, and I symmetry elements. This molecule is a non-linear, means C infinite V, D infinite H point groups are absent. Multiple higher order axis absent. Why only one C2, one proper axis, that is C2 is present, means TD and OH are absent. Any proper improper axis? Yes. C2 proper axis is present. So we have to go for the CN. Is C2 perpendicular to 2C2? C2 doesn't perpendicular to 2C2s. So we have to go for the C option. Here, in case of the trans-dichloroethylene, main order of axis is equal to 2. It means and sigma H is present. So we have to go for this C2, C2H, C2V, C2D. But sigma H is present, it means point group is C2H. Another molecule is this is non-planar hydrogen peroxide. This is non-planar hydrogen peroxide, or we can say cis hydrogen peroxide. This molecule consists C2 and 2 sigma V. E, C2 and 2 sigma V. So according to this chart, C2V is a point group. This is trans hydrogen peroxide or a planar hydrogen peroxide. This molecule consists E, C2 and sigma H. So point group is C2H. This is boric acid. Boric acid consists E, C3 and sigma H. So point group is C3H. This is phosphorus pentafluoride. The shape of this molecule is diagonal bipyramid. And this molecule consists E, main principal axis is C3. C3 is perpendicular to 2 C2s and sigma H. It means point group is D3H. Now, last molecule is cyclopentadiene. This molecule consists E, C5. C5 is perpendicular to 5 C2s and sigma H. So here, point group is D5H. So I think this is the point group of any molecule. How to find out the point group of any molecules? So, dear students, I think this is the enough for today's discussion. We will meet on the next session, that is with the help of the matrices and applications of group theory in these molecules. So, Khushbu madam, is it okay?
Thank you, sir. Thank you for taking time out for this webinar. Thank you, all the participants. And the session was very excellent, sir. And all the participants, we will share upcoming lectures link very soon. Thank you all. Have a nice day. Thank you, sir. Thank you
Thank you,
very
thank you,
much.
thank you, thank you, thank you.